What's up, my pre-calc people? I'm Michael Porinchak, and in this video, we're going to be talking about AP Precalculus topic 1.4 on polynomials and rates of change. Pretty easy, pretty short topic. We're going to briefly remind you what a polynomial function is, what it looks like graphically and analytically, and how we can understand the rates of change of a polynomial function and everything that we can learn from it. All right, so let's get ready to dive right into it right now. All right, so the first thing we have to do if we're going to explore polynomial functions is, well, understand what a polynomial function looks like. So here we go. A non-constant polynomial function of x is any function representation that is equivalent to the analytical form. Now, I know this looks rather confusing, but it's actually really simple, and I'm sure you recognize these. So basically, we have these terms. Every term has a x value with a power, x to the n minus 1, x to the n minus 2, and every term also has a coefficient in front of it. We're just calling it a sub n minus 1, just to differentiate between them. Now, the first thing is this, couple rules, that n is a positive integer, which basically means that you have to have x to something, either 1, 2, 3, 4, 5, for it to be a polynomial. You can't have it x being raised to a negative, that's not going to produce a polynomial, or it can't be x raised to 0, that's not going to be a polynomial either. Now, the other thing is that the coefficient a sub n on that first term has to be non-zero. Because if it was 0, then that entire term would be wiped out, and then all of a sudden you wouldn't have an x to the n. And then each coefficient must be a real number. So all these coefficients out in front of the x's have to be real numbers. Now, when we create this polynomial, we have a specific degree of that polynomial, and the degree is the largest exponent, right? And then it goes down the line. So again, this is a very, very generic form, but you could get the idea that if this degree right here was, like, say, a 4, then the next one would be x to the third, x to the second, x to the first, all the way down, technically to x to the 0. But x to the 0 is 1. Anything raised to 0 is 1, so we really don't have to even write that. And that's going to produce that last value, which we call our constant coefficient there at the back. Now, the very first term, that doesn't actually have to always be first, but the term that contains the largest power is going to be known as our leading term. So this entire value is our leading term. The n tells us the degree of our polynomial, and the coefficient in front of that leading term is called the leading coefficient. All right, it might make a little bit more sense if we look at some examples. So here are 4 different examples. All right, the first one is written nice in order. We do kind of prefer to write it in standard form, which means we go in order. So our largest degree goes first, there's to the 4th. Then we go down in our degrees, we go down the line. And again, this last one does have x to the 0, because I kind of like to think 4, 3, 2, 1, 0. But anything raised to 0 is 1, so you don't really need that there at all, because negative 9 times 1 is 1. Or excuse me, negative 9 times 1 is negative 9. All right, then we see that we have our coefficients out in front. That's the 3, the negative 7, the 2, the 5, and the negative 9. And again, this is our leading term because it's the first term. But again, it doesn't have to go first. It just has to have that biggest power on it. Now, you also don't have to have every power after that degree. So, for example, in this next one, we see 3x to the 4th, then we see a negative 7x cubed, but then there's no x squareds, there's no x's, and that's okay. It just means that the coefficient in front of them must have been 0. The only coefficient that can't be 0 is the one out in front, right here. Now, if that 3 was a 0, this entire term would get wiped out, and now we'd be down to a 3rd degree, if that makes sense. Now, the other thing to keep in mind is all the coefficients have to be real numbers. But don't think that fractions or square roots aren't real numbers. So here is kind of an ugly polynomial, but it's still a polynomial. So we got a leading term there of 3x to the 4th. That 3 is our leading coefficient. But then we have a negative 7/3, a fraction. Well, a fraction is still a real number. Then we have a coefficient of 2. Then we have a coefficient of radical 5 on that x. Again, very ugly coefficient, but radical 5 is a real number. That doesn't stop this from being a polynomial. And then here's another example where we don't have the leading term first. Standard form, it should go first, but it doesn't have to. But here we have that largest power, x to the 4th. So that's still going to be our leading term, even though it didn't come first. But it should be written in standard form with it in order. All right, so those are a couple of examples. And again, I know you guys have seen polynomials before, but they're nice and simple. Got to make sure you understand a couple of little different things there. Now, the first big topic that is in, or the first big concept, excuse me, that's in topic 1.4 is this. where a polynomial function switches between increasing and decreasing, or at the included endpoint of a polynomial with restricted domain, the polynomial function will have a local or relative maximum or minimum output value. Of all local maximum, the greatest is called the global or absolute maximum. Likewise, the least of all local minimum is called the global or absolute minimum. Oh boy, that's a lot to process. First, I keep it simple. Where a graph switches from increasing to decreasing is known as an extrema. These are where it makes a turn. It goes from increase to decrease or decrease to increase. Now, these could be local or relative maximums, or they could be absolute or global maximums, and same thing with minimums. Now again, reading all that might be a little bit weird, but keep in mind something really, really important. Not only is it where a polynomial function switches from increasing to decreasing, but if we restrict the domain of a polynomial, those endpoints also become extremas, or these local relative max and mins. Let me explain by looking at an example. It'll make a lot more sense. So here we have a quadratic polynomial, and we see that it goes increases and then it decreases. So it somewhere right around here, maybe negative, negative 2.5 is where we see that it has that extrema, we call it. Now, in this case, that point is the highest of every point in the graph. There is not a single point higher than that one, so we call that a global or absolute. You could use either phrase. I wish they would just stick with one, but different books say different things. So global or absolute, and that is a global or absolute maximum because it's the highest point. Now, we can also look at this polynomial right here. It's another quadratic where we see an absolute or global minimum. So once again, it's that lowest value, so we could call it absolute or global minimum. But in general, it's a extrema where we make that switch. Now, here's where it's important for me to comment on that little kind of thing I highlighted there. If we were to restrict this polynomial right here, we say, hey, we're only going to go from -4 to 1. That's the restriction. So we're only going to focus on the part of the polynomial that ranges from -4 to 1. Now, all of a sudden, we have 3 extremas. This is an extrema, this is an extrema, and this is an extrema. Now, this one down here at the bottom would still be considered an absolute or global minimum because, again, there's no value lower than it. But these other ones would be what we call relative extremas, or relative max or relative min, also known as local. Again, I know there's a couple different words we use there, but we say relative or local. Again, just like absolute or global. You could use either one. All that means is that relative to this area right here, this is a maximum value. And relative to this area right here, this is a minimum value. Now remember, we're restricting this from -4 to 1, so we're not even allowed to look at this other section over here. We're almost supposed to just ignore this part of the graph and this part of the graph, which again, technically does make those points at the ends what we would call extremas. Let's look at another example here where it's a little bit different. Here we see an absolute global minimum right there, somewhere right around maybe -2.1 around there, right? That's an absolute global minimum. But then we also see this point right here and this point right here. Now, it's kind of hard to see. You might want to zoom in there. But the idea is that those 2 points we do switch. At this first point right here, we switch from increasing to decrease. And then we decrease ever so slightly, but then we again turn around and increase. At those values where you switch from increase to decreasing, we have, again, what we call extremas. Now, these are not global max, right? This point right here is not the highest point on the entire graph because there's plenty of points over here and over here that are higher than it. But relative to its area in its own little neighborhood, it is a, well, relative maximum. Now, again, it's the difference between, like, if you think about, I'm pretty tall. I know you can't see that in the video, but in my classroom with 30 kids, I'm the tallest person. So I'm not the tallest in the entire world, so I'm definitely not an absolute or global maximum, but relative to the classroom I'm standing in, I am a relative maximum. So that would be considered a relative maximum, and this right here would be considered a relative minimum. Again, it's not the lowest point on the entire graph. There's plenty of points. In fact, there's this one right here that is the lowest point on the graph, but those would be considered relative minimum. So how many relative or how many total extremas does this graph have? It has 3. It's got that global absolute minimum, and it's got a relative max and a relative min. But don't forget the rule that I already said. If all of a sudden I say, let's restrict this from roughly negative 3.5 over here to 2, right? If I say, let's restrict this domain, so we're going to ignore all of this, going to ignore all of that. Now all of a sudden I technically have 5 extremas because those endpoints count as extremas. In this case, those would be relative maximums. All right, hopefully that makes sense. Here's another one. This is actually a similar one, just kind of zoomed in so you can understand and really see that there is that switch right here from increase to decrease and right here from decrease to increase. Those are, again, called extremas, but in this case, those are relative extremas. All right, so the next big concept in this topic is between every 2 distinct real zeros of a non-constant polynomial function, there must be at least one input value corresponding to a local max or local minimum. Okay, so first, let's get a couple things straight here. Let's go back, right? Technically speaking, a absolute min is still considered a relative min as well. They're one and the same because globally, to the entire graph, it is an absolute min, but relative to its area, it's also a relative min. So again, this graph technically has 3 extremas, which is very, very generic, but it's got a relative, 2 relative mins, and 1 relative max. But one of those relative mins is also a global min. So keep that in mind. When we talk about relative min and max, that doesn't disclude global or absolute. All right, so what we're saying here is if you have 2 distinct real zeros, there must be a local max or min in between them. So again, here's a graph, and we notice 1, 2 zeros, and notice in between there has to be a relative minimum or maximum. In this case, it's a minimum. Now again, you might say, well, wait a minute, is that an absolute? Well, like I already tried to state, a absolute or absolute min or max is also technically relative at the same time. And again, why does this rule needed? Well, it's just because when you cross through that 0, it's got to turn around at some point to cross this 0. I mean, how else is it going to get back up there unless it turns around and stops decreasing and becomes increasing? So we know that between any 2, there's got to be at least 1. So again, here's another example where we see actually 3 zeros. 1, 2, and guess what? In between them is a relative minimum. And then we see another one. Hey, look in between these 2. There is a relative maximum. And then here's another 0. And guess what? In between them is another relative minimum. So between any 2 real zeros, there's got to be at least 1 relative minimum or relative maximum. Hopefully that makes a lot of sense. Now, if you only have 1 0, well then there is not going to be a minimum or maximum in between. There's only 1, right? I'm not trying to say there's not going to be a minimum maximum anywhere in that graph. I'm just trying to say that like there's only 1. So this particular concept says in between any 2 real zeros. There's got to be 2 of them for this rule to kind of kick in. All right. Next concept in this topic is polynomial functions of an even degree will have either a global max or a global min. So if you have an even degree, 2, 4, 6, 8, 10, you gotta have a global max or global min. Now we're going to learn a little bit more about end behavior later on, but basically here is some examples of even polynomials, meaning that the degree is even. Degree is even. And when the degree is even, both ends have to do the same thing, whether both ends go up or both ends go down. But when that happens, there's got to be an absolute in between. Because if this thing's going to go down like this and then have to turn around to come up, or maybe it's going to do some other stuff in between, like right here, makes a couple other relative max or mins. But the point is, if both ends are doing the same thing, going towards infinity in this case, there's got to be an absolute value, an absolute extrema in between there somewhere. And in this case, we see 2 of them. Here's another one where both ends are opening down. And guess what? We do see this absolute global maximum in between. We also see some relative mins and maxes as well. But when you're an even polynomial, even degree polynomial, you must have an absolute max or absolute min. Now, what about odd degree polynomials? Well, odd degree polynomial will have no absolute max or mins. An odd degree polynomial, one end is going towards infinity and the other end is going towards negative infinity. So that means there could be no absolute max or min. Now, they may have relative or local max and mins, but they also may not. So the idea is that if you're even degree polynomial, you will have an absolute max or absolute min. If you're odd, you will not. All right, now the last big concept in this topic, and so again, like I said, fairly short topic, is that points of inflection of a polynomial function occur at input values where the rate of change of the function changes from increasing to decreasing or from decreasing to increasing. Not the function values, the rate of change. Meaning this occurs where the graph of a polynomial function changes from concave up to concave down or concave down to concave up. So here is a graph and we see that we are concave down and then somewhere we switch and we become concave up. Where we make that switch right around here somewhere is called a point of inflection. Now, hopefully you've watched my earlier videos and you know what concave up or concave down means. But again, concave down means that the rate of change is decreasing. So on this side, we see that we have a very, very positive rate of change, very, very positive rate of change, and then it becomes less and less positive, and then it turns the corner and becomes more and more negative. And that means that the rate of change is going down, which is why I'm concave down. But on the other side of that inflection point, I switch to concave up, where my rate of change is really, really negative, not so negative, and then it becomes positive and more positive, so my rate of change is going up, which means I'm concave up. That point in between is where we have a point of inflection, it's called. Now, how do you find that point of inflection? Well, right now, I just want you to be able to see it with your eyes. But in a lot of cases, it is directly in between a relative max or relative min, but not always. So don't always assume it's directly in between. Typically it is, but we don't want to make any assumptions yet. We just want you to visually be able to see it. Now here's another graph where we see that we make a couple changes, right? Somewhere right around here is a point of inflection. Again, we're concave up, and then on this side we're concave down. And then again, another point of inflection right here because we change from concave down to concave up. So I'm going to highlight the green part where I'm concave down, but everywhere else I'm concave up. So we actually see 2 points of inflection there. And what I decided to do here is actually zoom in on that so you can actually see that change right around here. Actually, let me get you a blue marker here so you can see a little better. But right around there, we see that change from concave down to concave up. So that's definitely a point of inflection. And like I said, just want you to be able to see them right now. Now here is a quadratic or a polynomial of degree 2, and this has no inflection points. So you might have inflection points, you might not. This graph is entirely concave up. Yes, the outputs are decreasing and then increasing, but it's concave up the entire time. It never switches concavity. The rates of change are going up. They're really, really negative and less negative, and they actually become zero down there at the bottom, and then more and more positive. So the rates of change are going up, so it's concave up. There are no points of inflection. All right, that's it for the big concepts in topic 1.4 at AP Precalculus. Overall, not too difficult. Now you just got to work on some problems to practice those skills.